Hey, and it's a pleasure to be here. So actually, I'm going to talk about, basically, I'm interested essentially in the geometry and dynamics on moduli spaces. This is the general theme, but I'm going to just talk about a certain aspect of the theory which I thought about it. So let me just also set the ground. I wanted to think about SGN, which is a genus G surface. So let's say orientable. Surface with n punctures, and the Teichmüller space of this surface, which I'm going to denote it by TGN, is just a space of we can think about as marked hyperbolic, or let's say complex Riemann surfaces which are homeomorphic to this surface. So just think about a marking, which is a homeomorphism from SGN to X, where X you can think about it as either a complete hyperbolic surface or a complex Riemann surface, and just consider all of this marked Riemann surfaces, and that's the Teichmüller space, and also the mapping class group of the surface, which is the group of the orientation, again preserving homeomorphisms of the surface, acts on this space up to isotopy, acts on this space just naturally by remarking. So I just write it as the action of the mapping class group, and in the quotient we have just a moduli space of Riemann surfaces, which I would like to talk a little bit about that. So also the picture which one should have in mind is that, so just think about it as having a manifold and orbifold and its universal cover, and I would like to think about the geometry or dynamics on this manifold. And just let me give you one example. When, in the case of once punctured torus, I guess everybody has his own way of thinking about that, or the Teichmüller space of this surface as the upper half plane. So you have two real degrees of freedom if you think about the differential Newton coordinate, or maybe one complex parameter, and that gives us the upper half plane, and the mapping class group here is just SL2Z, which acts on the upper half plane, and we have this the picture of the standard tessellation of the upper half plane by the action of the SL2Z. So let me just draw the picture here, maybe -2. So, and so we'll just draw these lines here is I, and the fundamental domain for this action is going to be this region. So the imaginary part is between the real part is between 1 and -1, and we consider the region which is outside this disk, and then when we're acting by SL2Z, which I can. It's essentially generated with this two elements, 0, -1, 0. I want to pick these two generators, which act as Mobius transformations here. So here this is going to be Z is going to Z plus 1. Sorry. And this is going to Z goes to -1 over Z. So we get a tessellation of this the upper half plane. So it's going to be a picture which looks like this, and we can continue this picture and get a tessellation, and of course the quotient is the. So let me just again draw my picture like this. So it's called the modular surface, which is a surface with one cusp and two singularities, which correspond to this point and the point at infinity. So this is going to be the M11, and it's called the modular surface. So first of all, is there any question at this point? No. Okay, so then, now let's say I'm interested in geodesics. Let's say just think about this tessellation and upper half plane, and let me draw a geodesic, maybe something like which looks like this. So this is a geodesic R, and its endpoint is a point along the real line. And so one way of coding this geodesic, which is a fairly classic, is to keep track of the regions which the regions in the tessellation which this geodesic intersects, or equivalently keep track of the elements of the mapping class group, or SL2Z, which bring that tessellation to the one which we started with. So if I think that way, and let's call this element L and this element R, we get the cutting sequence essentially for the sequence. So we might have we may need to apply a couple of these elements. So let's say we have some number of L's, and then maybe we start applying R and so on. So let's say I have N knob, M1, and so on, some number of L's and R's, and this is called the cutting sequence. For let's say R. And so there is a nice relationship between these numbers which I see here. So let me list them: N1, N naught, N1, N2, and so on, with the continued fraction expansion of this endpoint. So in other words, the x is going to be 1 over, let's say, N1 plus 1 over N2 plus 1 over N3, and so on. So this is a picture which was given by maybe Artin and series, and sort of very classic. And so first of all, is there any question? So this is N0 doesn't appear. So for the backward, you need to include N naught. And there's a little bit of a line in this picture. So one actually needs to consider the Ferry graph of the Ferry tessellation, which corresponds to the covering of a degree 3 cover of the modular surface. And there, this correspondence, this keep tracking of the regions and the continued fraction actually matches. This is actually correct for that, but I just wanted to simplify the picture. And so one can also write some interesting statements just based on this picture. For example, one of this, if you are interested in when the geodesic, so let's say this is the universal cover, and you go to the your manifold. So there are statements like this, that if, for example, if this sequence Ni from 1 to infinity, let's say, is bounded, let's say, then the ray, so let me just, then R is co-bounded, which means that it projects to a compact part of the moduli space. Also, for example, if you see a string which repeats in the continuous fraction expansion, then you actually you have a geodesic which is recurrent to a compact part of the moduli space. So this is some sort of coding. And So now let me just briefly tell you what are there are two. So this was you can think about this as a kind of basic example of a modular space and the Teichmüller space. But there are two. I mean, there are various metrics on this space. So let me just mention two of them: the Teichmüller metric and the Weil-Petersson metric. So I'm not going to explicitly define them. What's that? They agree in this example. Yeah, they agree in this example. Essentially, this or maybe the Ferry tessellation actually is going to be tessellation by geodesics of both of these two metrics. And the Teichmüller, for the Teichmüller metric, so let me just list some of their properties so rather than defining. So this is a Finsler metric, and it's incomplete. So these are some geometric properties of this metric. Also, it's right. Sorry, it's complete, but it's not negatively curved in any of the senses. Maybe in the sense of Gromov or Boozman, it's not negatively curved. Also, for example, let me say a couple of its coarse properties. For example, it's higher rank, again in the sense of Gromov, and it's, for example, it's quasi-isometrically rigid, and so on. Also, from the dynamics point of view, for example, the geodesic, the Teichmüller geodesic flow is ergodic and has exponential rate of mixing, and so on. For Weil-Petersson, let me just say that it's Riemannian. Is incomplete, but is this what this time it's this is negatively curved. It has from the coarse point of view, it has a cat zero completion. No, they don't quite agree, but this so this is just the geodesics on the bound. This tessellation is going to be the tessellation by geodesics. So they don't. They're not exactly. They're not.
It's always true that this one is incomplete and the first one is complete.
Right. Even in that case. So in the case of M11. Also, so again, so this is also going to be higher rank and quasi-isometrically rigid. So these are interesting metrics, and they have different features. But again, as was mentioned, this picture provides essentially what I described, provides for a kind of symbolic coding for both of these two metrics. In the case of M11, but let's say what I want to talk today, so maybe just indicate that so what we do when we are in the case of, let's say, some higher genus surface. So here, I need to introduce a couple of notions. The first one is the curve. So actually, this is one of the approaches, but so this the curve complex of S. So it's also introduced by Harvey in the 80s. So or let's just think about the curve graph of the surface. So it's a graph. So I need to tell you what are the vertices and what are the edges of this graph. The vertices of this graph are the homotopic classes of simple closed curves on S. Also, they are essential. They are not homotopic to the punctures, and the edges of this graph correspond to disjoint pairs of simple closed curves. Okay, so let me draw maybe a simple picture also. So let's say this is my surface, and let's say I have this curve, and maybe this curve. So let's say alpha, beta, and gamma. So there are infinitely many simple closed curves, of course, on our surface. But
There's at least one function.
no.
It might be zero.
Yeah, the number of punctures. But again, you can, I mean, as long as the genus is greater than 1, you can still have hyperbolic metric answer. So, and this is gamma, and sort of by this description of edges, so there is an edge between alpha and gamma and beta, but there is no edge between alpha and beta. And it turns out that this is, let's say, an infinite graph, which is also locally infinite and quite a complicated object. But so also we can turn this graph to a metric graph by just assigning length 1 to each one of the edges. So now we have a metric graph. And let me mention this result of Mazur and Minsky. Around 2000, that this curve graph, so let me denote it by CS, is Gromov hyperbolic. Okay, so should I use also this, or okay, so, or maybe the other? Oh, all right, sure. I can just switch to this.
You really want to keep that top thing? That one?
No, actually, there is no.
No, you can bring it back down once it goes up. It's allowed it to come down.
Right. So, okay. So, just kind of. So now let me tell you how to use curve complexes to develop something similar to what we saw in the case of the modular surface. So in this case, just remember, so when we think about, let's say...
So C of S denotes the curve graph? I mean,
yeah, so that's my curve graph, so let's put it here. Right. So here, let's pick your favorite ray, let's say Teichmüller or Weil-Petersson geodesic ray. And remember every point, so and now also let's adopt the hyperbolic point of view that every point is a hyperbolic surface. And let me just, so at every point, so at any time along this ray, I have a surface. So let me just draw it, something like this. So this is maybe my surface here, and maybe when this is a genus 2 surface, so let's say, and let's say when I reach here, I have something which looks like, so let's say this. So, and the idea is to keep track of short curves along the ray. So for example, here I have, let's say, this short curve, but here this curve is short. And let me draw the curve complex like this. So then I have some initial set of short curves, so which are finite, and let's say is this point. And as I kind of travel along the ray, I get sort of bounded. So each various points in the curve complex, and if so, that it could let's say look like something like this, or if you're maybe lucky, so it's limits to something at the boundary of the curve complex. But remember also the curve complex is a Gromov hyperbolic, so it has a natural boundary. And again, by a result which to student of Minsky, Clarice, so the boundary, you can identify the objects on the boundary as laminations on the surface. So these are laminations are just partial foliations of the surface, foliation of a closed subset of the surface with geodesics. And then now I'm almost at the point to tell you what's the analog of the digits which we see in the continued fraction expansion. So let me again draw my surface. Let's say it looks like this. So, and let's pick any of the subsurfaces of the surface. So let's say this is y, and let's say in mu, which was the set of short curves at the initial point of my array. So let's say I have this curve and this curve. Okay. So I picked these two curves, and for lambda, as I said, is a lamination. So it consists of maybe infinite leaves or infinite geodesics, and you can always fix a hyperbolic metric as the background metric. So then let's say we get maybe a leaf which looks like this, and maybe it goes like this and sort of winds around and goes somewhere. So this is a part of lambda. And now the idea is to just intersect. Let's say I have these two white curves. I intersect. So this curve is already inside Y. This other curve intersects the boundary. I can close it up by picking one of the sub-arcs on the boundary. So I get, let's say, two curves which are inside the curve complex of Y. And so let me call that pi y of mu, the subsurface y subsurface projection of mu. Similar for lambda. So pick the leaf and just complete it to a closed geodesic, and I get the projection of lambda. And now just measure the distance between these two in the curve complex. So then, so if I measure this distance, it's going to give me a number. So I'm going to call this, so this distance, let's say in the curve complex, this is going to the subsurface coefficient. And I'm calling this the subsurface coefficient, the y subsurface coefficient of mu and lambda. And the point is that now I have, so again, my surface has just one minute. One, okay. So that has infinitely many subsurfaces. I just list all of them. And this is going to be the list of numbers which I look. And so let me just maybe state one statement which is quite similar to what we saw at the beginning, that if this is bounded, so if let's say this is bounded, so as you vary the subsurface is bounded, then the geodesic this ray I started with and produced this mu and lambda and look at its coefficient, then the geodesic ray again is co-bounded. Also, you can play with this game, so produce various condition for recurrence. For example, if I just bound also for both of the metrics. Also, if I bound all of the subsurface coefficients except the annular ones in the Weil-Petersson setting, that is equivalent. That implies at least the recurrence of the ray and into some compact part of the modular space, and many sort of analogs of the what we had in the setting of continued fraction expansions also hold here. Thank you.
What does co-bounded mean here?
Co-bounded again means that when you project it to the modular space, it stays in the compact part of the modular space.
Could you explain the cutoff again?
How do I project?
Yeah, how do you get this number? The distance, but how do you get those things?
So just so let's say you have this simple closed curve on your surface. Just let's say in this picture it has two intersection points. Just pick this and one of the arcs in the boundary of Y, such that their concatenation is closed.
Yeah.
So you can.
Blue one.
What's that? For the blue one again the same. So you have this when you pick one of the leaves, and all of these things are up to isotopy. So I mean, if you have a bunch of kind of things which travel parallel, which are parallel to each other, they are going to be eventually identified. And these are going to be bounded diameter subsets of the, actually bond diameter 2 subsets of the curve complex. So there is no ambiguity in defining the distance, as long as you start with the lambda.
So the blue line is disjoint from the white line when you cut it off?
The boundary or the other, it doesn't. It's not necessary for here. It intersects that. So by white you mean the.
But you want to have that distance to be finite, so you need arc in the curve. You need a path in the curve complex.
That's correct. So right now, these are two going to be 2 points or 2 bounded diameter subsets of the curve complex, and then you measure their distance.
example?
Which one did this?
You know, at first you gave us example.
Yeah, so again, so he did, I mean, there's very explicit, so then you can apply these elements of the map, so you kind of think about, you have these two elements of the map.
So what is Y?
What's, yeah, so you need to fix, let's say, two, or let's say one curve on my surface, that's an analysis. And then when you apply these elements of the mapping class group, that's going to be several annuli on the surface. And those are subsurfaces. And here I didn't define the subsurface coefficient for an analysis, but it's more or less similar to that. So again, so there is a kind of exact analogy, and sort of you, again, you produce the sequence of the subsurfaces just by applying elements of mapping class group to just one analysis.
Thank you.